provide quality of electrical power to your customers, right? Right, that quality of power is now getting affected due to the major two things only. Now, power factor as well as harmonics. So due to two majority things like quality of power is getting disturbed, right? The two things is, one is a power factor, one is now harmonics. So power factor is how it's just getting disturbed, right? So we have discussed briefly in our electrical management and electrical motor side, while just we have discussed many things. So due to inductive loads and capacity loads, the power factor is now getting affected. And how it's going to eliminate, right? So we're just going to go with it. One second, please wait. This is my call. One second, sorry. Okay, sorry. It will continue. Uh, where we have passed, right? So due to those things, right? The quality of power is getting affected. So due to harmonics and power factor, right? And today we're just going to especially see about lighting loads. So due to lighting loads, how the power is getting affected. So last class we have discussed about some standards, right? So standards for manufacturing, right? So these are the standard which we just to focus in our previous classes, right? So based upon these standards, some policies and regulations will be there. Some associations like IEC and IEEE, NEMA, ANSI, right? So these are the notable standards for lighting loads, right? So these are the standards which consist of rules and regulations, right? So these are the limitations, right? So while manufacturing itself, right? So they will go with it. Now we have discussed about these things. Now I'm just straight away moving into different type of lighting loads and how they just introducing a power factor as well as how just introducing harmonics, right? So I'll go with the fluorescent lamps, right? So we'll already know about two types of fluorescent lamp we are just now currently we are using. One is a magnetic ballast type, and we'll have one more. Nowadays we are having a electronic ballast fluorescent lamp, right? We are using currently we are using two types of fluorescent lamp. So like around 2.5 meter length, right? We'll have two types. One is now magnetic ballast type, that is called just now I'm just going to show you, right? So magnetic ballast type fluorescent tube light, and will with the help of starters, right? You will have one more. Nowadays we are having electronic ballast over this copper ballast, right? So we'll have two types of thing, right? So actually there is a the working principle already people well known, right? So this is called working under principle of AC power supply, right? So phase neutral, so we're just going to give it. So for this we'll having a number of types of lamp over here. We'll have white light, green light, purple color. We'll have based upon that. So based upon that uh, vapor powder is now coating, right? So we'll have white color, that is called phosphorus, right? So we'll have phosphorus something, they will have potassium. So we'll have different types of powders when will be over poured into this tube, right? So based upon that, it will have the different types of lighting output, right? Now we'll have over there, right? So we're having two lamps at the end, right? So one here and this one. That is my anode. This is what my cathode. So we're just going to ionize this entire thing, right? So we're just going to ionize this tube, right? So எப்படி பண்றதுன்னா, we need to apply more voltage on my anode side or maybe cathode side. So we're just going to go with the anode and cathode. So we're just going to apply more voltage over here. So due to the more voltage, now the electron is getting started to flow from this anode to cathode. So this entire tubular it start to flow. So அந்த அவ்வளோ வோல்டேஜில் கிரியேட் பண்ணணும். பட் மை சிங்கிள் ஃபேஸ் வோல்டேஜ் வி ஆர் ஹேவிங் ஒன்லி 230 வோல்டேஜ் சிங்கிள் ஃபேஸ் வோல்டேஜ். ஸோ இந்த வோல்டேஜ் எனக்கு இட்ஸ் நாட் எனஃப் டு analyze this entire thing, right? So it needs some boosting mechanism over there, right? So for that purpose, there is a magnetic ballast over here. So we already know sort of that magnetic ballast. So a number of copper coil is now wounded on a iron pieces over here. So it will going to introduce boost voltage, right? So we'll have that thing over here, right? So now we could see we are having a copper ballast, so you could able to increase your voltage due to by dA by dt. LdA by dt you could able to convert into flux lines. Flux lines is now again is now going to be applied over here. So you could able to increase your voltage around 1000 voltage. You could able to boost about 1000 voltage at the starting time alone. So நல்லா வாட்ச் பண்ணி பாருங்க. ஸோ அப்போ நீங்கள் கேட்கல சார் இப்போ ஸ்டெப் அப் பண்ணுறோமா அப்படின்னு கேட்கலாம். டெஃபினெட்லி வி ஜஸ்ட் ஸ்டெப் அப். பட் ஒன்ஸ் தட் லைட் இஸ் நவ் ஸ்டார்ட் டு glowing, right? So the light வந்துட்டு start to glow ஆயிடுச்சுன்னா அந்த வோல்டேஜ் எனக்கு அவ்வளோ இருக்காது. It will be normally reduced into 230, right? Because current is now flowing over here, right? Current வந்து இங்கே ஃப்ளோ ஆக ஆரம்பிச்சிடும், டிஸ்சார்ஜ் ஆக ஆரம்பிச்சிடும். அப்போ எனக்கு மோர் அமௌண்ட் ஆஃப் கரண்ட் இங்கே ஃப்ளோ ஆகாது, அப்போ ஃப்ளக்ஸ் லைன்ஸ் கண்டிப்பாக ஜென்ரேட் ஆகாது, வோல்டேஜ் வந்து ரெடியூஸ் ஆகிடும். தட்ஸ் வை. ஸோ இங்கே லைட்டிங் ஸ்டார்ட் பண்ணுறவங்களும் தான் தட் மச் வோல்டேஜ். ஒன்ஸ் த லைட் இஸ் நவ் ஸ்டார்டட் க்ளோயிங். லைட் ஸ்டார்ட் ஆயிடுச்சுன்னா என்ன அர்த்தம்? லைட் க்ளோ ஆயிடுச்சுன்னா என்ன அர்த்தம்னா எலக்ட்ரான் இஸ் நவ் ஃப்ளோயிங் ஃப்ரம் ஆனோட் டு கேத்தோட், ரைட்? ஸோ இங்கேருந்து இங்கே ஃப்ளோ ஆக ஆரம்பிச்சிருச்சு. ஸோ அப்போ எனக்கு இங்கேருந்து கரண்ட் வந்து இங்கே டெலிவரி ஆக ஆரம்பிச்சிருச்சு, ரைட்? ஸோ அப்போ எனக்கு இங்கே அதிகமாக கரண்ட் இருக்காது. ஸோ தட்ஸ் அதிகமாக ஃப்ளக்ஸ் வராது. தெர் இஸ் நோ மச் வோல்டேஜ் இஸ் நாட் கோயிங் டு பி பூஸ்டட் அப். ஒன்ஸ் ஸ்டார்டிங் டைமில் மட்டும்தான் தட் மச். So due to this inductive type of coils, definitely my power factor is now somewhat it's getting affected, right? So this is one thing. And we'll go with it. We'll have different types of thing, right? So this is my yellow color, right? So this is my yellow color. It denotes that my input voltage 260 around, right? And my this thing, right? So this blue color core, it's now my boosted lamp voltage exactly. And this my gray color is denotes that my current. You could see there is a phase lag between my starting period பாருங்க, இங்க voltage எங்க இருக்கு, current waveform somewhat lagging. That's called power factor. It will be now it's getting creating, right? So now it's power factor is now somewhat it's getting delayed. This much power factor is now getting introduced to my due to these things. So now actually what actually they will do nowadays we will have electronic ballast. We are just going to using the same type of this mechanism. So இவங்க என்ன பண்ணுவாங்க அப்படின்னா, we'll see we'll have that electronic ballast over here. See, so electronic ballast order diagram this one, right? So we'll have electronic ballast over here. So line input voltage we are just going to give. So I'm just going to discuss EMI filter and later. So electromagnetic inference filter, this full form electromagnetic inference filter with the help of shunt capacitor and the series inductor types of system will be there. So we'll discuss later. So now input voltage, that is called my phase neutral AC voltage, is now applied to my bridge rectifier. Is now totally converted into direct current, right? Again the direct current is now converted into DC current, is now again converted into my AC current into this my lamp, right? So this is what my lamp. Again we are just going to convert it into AC in sometimes. So in some of the thing will be they directly utilizing DC current also. But inga pathina 50 hertz power supply, right? So we'll have 50 hertz power supply, but in my lamp side it will be around 2 kilohertz. You could have that idea. So now in my input power supply 50 hertz, but at my lamp side it will be now 2 kilohertz power frequency. Here we'll have a 230 voltage input voltage, but in my lamp side it will be around 15 volt or maybe 25 volt. It will be somewhat very low voltage, right? You could have that a clear idea. Now we'll have input voltage 230 in my input side. My lamp input side lamp around 25 volt generator, but my frequency it will be now 2 kilohertz instead of 50 hertz. The same way current it will be based upon my load. You could see I'm just going to give you that, right? So overall introduction, right? So now is one second. So the advantage of electronic ballast is that high frequency operations is available. I already told that it's around 2 kilohertz to 5 kilohertz. So some manufacturer, right? So some of the manufacturer they will go with it up to 5 kilohertz. So up to 5 kilohertz, they will go 2 to 5 kilohertz. They will go. That's why I already told that. So advantage of this electronic ballast is high frequency operation at electronic ballast, right? So these things will be available. So this one electronic ballast we could see choice of frequency of electronic ballast. It will be look like this is a standard thing. So I already told that. So for 60 hertz power supply, they're just going to convert 1 kilohertz to 20 kilohertz. I already told that. So 2 to 5, but the 60 hertz they will go beyond that also. The electronic ballast typically operate frequency between 60 kilohertz up to 20 kilohertz to 60 kilohertz based upon the load size of your lamp size, right? We'll have a mercury lamp, we'll have a T8, T12, T5, we'll have different types of lamp. So that's why it's now 20 kilohertz to, that's called as 60 kilohertz also they are using. So the frequency, right? So we are changing the input frequency of a power supply, right? So இதனால என்ன சார் ஆகும்? Right now see, in my magnetic ballast only power factor is going to be getting affected. You could see. So we are just going to use inductive type of load over here. That's why my power factor is alone is now getting changed. So due to that, quality of power is also getting affected. My lamping fluorescent lamp. The same way, instead of copper ballast, we are using electronic ballast over here. If you're just going to use electronic ballast, so definitely அப்போ என்ன ஆகுதுன்னா, so we are just going to reduce in நல்லா வாட்ச் பண்ணினா தெரியும். இது ஒரு 40 watts இருக்குன்னா, for example 36 watts 40 watts, if you are having a right idea, right? Having an idea, it will be around நீங்க மார்க்கெட்ல போய் பாத்தீங்கன்னா தெரியும், fluorescent magnetic ballast பாத்தீங்கன்னா 40 watts bulb இருக்கு. Now electronic ballast it will be around somewhat very low power, right? So it will be very low power. It will be around 26 watts கீழே தான் வரும். இது total power, right? It will be 26 watts கீழே வரும். But anyway, I'm just going to show that final comparison. You could see electronic ballast supply input voltage is now 50 to 60 hertz. My output is now 20 kilohertz to 80 kilohertz. The same way, it will be magnetic ballast. It will be around 1000 voltage boost starting time, right? So up to after that, once the light is now started, that called the discharging process. Anode to cathode, the electron is now started to flowing. So anode to cathode, the electron is now started to flowing. It shows that current is now flowing from anode to cathode. That's called discharging is now started. That's time light is now illuminating. So that time the voltage is now reduced to up to 125 volt in electronic ballast, right? So that's why, right? So starting la mattum dhaan this much voltage is needed, but after starting we are just going to reducing this voltage. Definitely current is also getting limited, voltage is also limited. So my power consumption also is going to be very low. So that's why I already told that. So இது எல்லாமே எனக்கு எலக்ட்ரானிக் கண்ட்ரோல்ல எல்லாமே வந்துடும். ஸோ சிம்பிளி எனக்கு வந்துட்டு இது எலக்ட்ரோமேட்டிக் இன்டர்ஃபரன்ஸ் ஃபில்டர் என்னன்னா, ஸோ மை இன்புட் வோல்டேஜில் வர electromagnetic interference and radio waves எல்லாமே என்ன பண்ணணும்னா ஃபில்டர் பண்ணும். It's like a filter, right? It's going to filter and it's going to allow a pure sinusoidal wave over here, right? So it's going to convert into pure sinusoidal over here also, right? This thing, and we'll go with it, right? So this thing, right? So my magnetic ballast only my power factor is going to be only affected. but my electronic ballast, right? So we are just going to convert about 50 hits power supply. We are just going to convert 50 hits into, we are just going to convert it into 5 kilowatts, right? So 5 kilowatts or 60 kilowatts. I'm just going to consider 10 kilowatts now. 10 kilowatts. So we people already discussed about power electronic switching devices in our power electronic subject, right? So அதில் so right powertronic we'll have discussed about my MOSFET and IGBT or SCR. So these are the switches is now is going to be act as an inverter. So right fast switching speed MOSFET and IGBT they are also utilized over here. So they just going to convert this much, that is called my cyclo, that's called my cyclo converters, right? So step up பண்ணிருக்கு, right? 50 hertz 10 kilohertz change இருக்கு, that's called this much switches is now going to be turned on, turned off, turned on, turned off. So due to this, right, so there is a one more effect is now going to be introduced, that is called harmonics. Now due to this switching transition things, right, so we are just going to convert 50 hertz into 50 kilowatts, right? That's why due to this switching operations, my in my network now harmonics is now getting introduced. So due to my power electronic devices, switching devices, right? So due to electronic ballast load, right? Harmonics is now getting introduced instead of huge power factor issue. Here, harmonics is now introduced because we are using switching devices over here. So electronic ballast use பண்றப்ப எனக்கு என்ன ஆகுதுன்னா harmonics is now getting introduced. That's why I'm just going to focus to it now. So this is what my thing. So right, so electronic ballast, front end no filtering, no power factor improvement. So this diagram, so no power factor correction, no more things. It simply will have a resistor, AC input. AC input என்ன பண்ண போறேன், so we are using bridge rectifier, we are just directly converted into DC output. Now my will, this is a standard thing. So nowadays, so they are using filtering operations, right? So we using that is called nowadays manufacture பண்றப்ப இதெல்லாமே manufacture பண்ணிடுறாங்க. That is called my passive filter, right? So power factor improve பண்றதுக்கும் சரி, harmonic reduce பண்றதுக்கும் சரி, they are just introducing this two, but L and C is now connected before my bridge rectifier. So this is called LC filter, right? That is called my passive filter is now connected with my before input, right? So nowadays they are using right now. So before olden days they are not using, only they are using a resistor for limiting input current only, they are just introducing. But nowadays they are using a filter. So you could have that in your electronic ballast இப்போ பார்த்தீங்கன்னா தெரியும், nowadays fuse பண்ண பல்ப்ல எடுத்து பாருங்க. So before power supply, this one, these things will be available. Before that there will be a step down transformer will be there. So before that there is a step down transformer, after that filter, after that rectifier, again there is a one more capacity filter, then just have a after thing, right? So cyclo converter will be there. So now we'll have converters, they'll have like these things, right? So electronic ballast without filter. So this is one type of example. Anyway, we are just moving little fast, right? I'm not going to much more into that. So input power supply, filter, rectifier, DC filter. After that we'll have inverter circuits. We'll have inverter circuit over here. So D1, T10, D9, and we'll have D8. So T6, and one more thing where actually T1, T1, 2, T1, T2. So by switching on these devices, right? Switching devices, you could see, right? So which these things you could able to change your input frequency and based upon your load. Here also will be, you could see one more with filter, here without filter, here with filter, LC, L2 and C6, that's called my filter, and L1, C1 is my input filter. Here also, here output filter, right? So now we'll have that these things. Now we'll have IC. So in the IC என்ன பண்ண போதுன்னா, it's going to create a gate pulse towards this thing. So you could see, you could find out the symbol, you could see the symbol is now gate driven, right? So now you could see T1, T2, right? So timing IC, it will generate a gate pulse, it's going to trigger on this T1 and T2 based upon internal programming, right? So internal microcontroller program, it's going to work, right? And this my CFL bulb over here also. So you could see that internal diagram, right? So compact fluorescent lamp thing. So step down transformer will have inductor and capacitor, that's called the input filter, and will have a rectifier also over here, right? So these are the things, it will be in things which I just got from ABB input data. We'll see next thing. We'll move into a little bit forward. Before into that, I'm just going to show one small video. I think I'm just going to move with that 1 second. So this is exact fluorescent order exact hardware. So we'll have front end over here, we'll have output over here. We'll have two types of thing. So we'll have two types of output in my front end side. So step down transformer. After that, we'll have a rectifier. After that, we'll have a capacitors, resistors, and then we'll have ICs. Then finally, output will be over here. So we'll have two types of input. So this is what my lamp. So we needed two circuit. So either lamp எனக்கு வேணும், இந்த lamp வேணும். That's why two types of circuit. Front one more lamp, one more lamp. My switching devices here, here. This is what my IC, ICB2FLG03. Google அடிச்சு பாருங்க. So ICB2FLO3G. This model IC எதுக்கு யூஸ் பண்ணாங்கன்னா கூகுளில் பார்த்தீங்கன்னா டேட்டா சீட் கிடைக்கும். அந்த டேட்டா சீட்டில் what actually it will does do. So it will generate HSGSD and LSGD. That's called gate. This is my higher thing and lower IC. ஸோ எனக்கு கேட்டுக்கு ட்ரிவன் சிக்னல் வித் த்ரூ ரெசிஸ்டர் வழியாக எனக்கு கேட் ட்ரிகர் இங்கே பல்ஸ் வருது அண்ட் இட்ஸ் கோயிங் டு பி ஜெனரேட். ஸோ வில் ஹாவ் ஒன் மோர் திங் ஓவர் ஹியர் அண்ட் so 54 watts T5 single lamp design with voltage mode preheating 54 watts lamp is now we are using over here. And active power factor correction, we'll go with the two types of power factor correction. Already in our power quality subject you people studied about active filter and passive filter. So right, so I think Ramesh Kumar sir told that, right? So active filter and passive filters. Syntactic filter, actually he is done his PhD on syntactic filter. Anyway, he just discussed about, I guess he discussed, I think, right? So anyway, you're just going to see. I'm not going to much detailed into that, right? So I'm not going to move with that. So anyway, I'm just going to give you entire thing, right? So overall about those things, right? And after light is now getting eliminated after 30th minute operation, that efficiency of your lamp is now getting about increased about beyond 93%. But starting time it will be very very low after 30 to 50 minutes, right? So it will going to reduce entire harmonics, power factor correction, everything is now going to be done with the help of these ICs, right? So nowadays, so lamp குள்ள இவ்வளவு பெரிய காம்ப்ளிகேட்டட் சர்க்யூட் இருக்கா சார் அப்படின்னு கேட்டிங்கன்னா எஸ், இட்ஸ் டெஃபினெட்லி nowadays, ரைட்? இந்த மாதிரி லேம்ப்லாம் வந்துட்டே இருக்கு. ஸோ ஓல்டன் டேஸ் ஒன்லி ஒரே ஒரு காப்பர் பல்லாஸ்ட் மட்டும் தான் இருக்கும், நத்திங் இட் வில் பி மோர் தென் தட், ரைட்? ஸோ ஒரு ஸ்டார்டர் இருக்கும், ஒரு நவ டேஸ் வி ஆர் ஹேவிங் திஸ் மச், ரைட்? ஸோ திஸ் மச் திங்ஸ் வில் பி அவைலபிள் இன் லைட்டிங் சிஸ்டம், ரைட்? Now I'm just going to give you, right, what is meant by exactly harmonics. So if people already much knowledge on over harmonics, anyway I'm just going to give you what actually harmonics, right? So these are the things will be available AC, and we are just going to convert the AC into DC, and again we are just going to convert it into AC. So now we'll see the voltage waveform will be look like this, right? So the normal voltage will be look like this, AC input voltage. Now after switching devices, right, so we are getting a what could I say, we are just getting after a rectifier and inverting output, right? So we'll have a current like based upon my load, the current will be look like this. And current pathina, it's not again pure sinusoidal waveform, it's not again pure sinusoidal, it will be somewhat this thing because of due to my switching things, due to my switching devices, right? My voltage waveform and current waveform, it has some disruptor, right? That's why. So it will be look like this, right? Anyway, I'm going to, this is a real time thing, so which is captured from a scope of power scope analyzer, right? So my voltage, it will be look like this, my DC voltage is now look like this. Somewhat it's not a pure DC, as well as it's not going to be pure current. So there is a huge error is now நிறைய ஒரு up and down spike இருக்குல்ல, we will see. So due to these things is now due to my switching devices things, so due to my MOSFET or Jeff maybe MOSFET or IGBT, due to my switching devices, switching transition time, so my input voltage is also getting affected. So we are giving input voltage over here, right? So this also getting affected. So due to my switching devices, we'll see here also we'll be having a control ICs over here. This control IC is going to be generate a control pulse that's called gate pulse over here, right? Anyway, I'm just going to discuss about those things. Straight away, I'm just going to move with that these things. So we'll have before going directly into harmonics, I will have different standards for driver circuits. Now commonly we are having ECN, one more company, right? So they are just given some what could I say, useful content into that, right? So how we are just going to manufacture useful driver circuits for LEDs, right? So we'll see. So before moving into LED, I'm just looking into one small video. You could easily understood, right? Before LED, right? So before LED, I'm just going to finish it off for my harmonics. We'll after that we're just coming into LEDs. One second, I'm just looking for a small thing. Now I'm just going to share one small tab. You could easily understood. I'm just going to phrase it over here. There, it's could easily understood the harmonics. Already people studied. Anyway, I'm just going to recall it 1 second. That's all. I think my screen is visible, right? So harmonics is nothing but it gets introduced by what could I say? My switching devices, right? So based upon my switching device only, the current is now getting consumed by a load, right? So we are just already told that. So based upon my switching devices, based upon my load, right? So we'll have different types of frequencies, right? We are just going to convert about 50 hertz power supply into 50 kilohertz, right? Based upon my switching devices gate pulse, right? So now we'll see that.
Critically important concept in electronics. Harmonics affect the quality of AC electricity delivered to homes and facilities, and the performance of equipment that uses this electricity. Harmonics can increase energy costs and reduce the lifespan of hardware. In some cases, harmonics can overheat electrical conductors, creating a fire risk. In this video, we briefly explain what harmonics are and why you should care about them. To begin, let's consider a mathematical concept called the periodic wave. This is a graphical representation of a constantly changing variable whose values follow a repeated
So this is what my voltage waveform, right?
sequence. A familiar example is the sine wave shown on the screen. When we examine a sine wave, one of the first things we notice is that it follows a very symmetrical and repeated pattern. Each full wave has a certain length, called its wavelength. The time required for one wavelength to complete a cycle is called its period, from which we derive the term periodic wave. Periodic waves are found in a wide variety of natural phenomena, including ocean waves, sound, and light. Electricity transmitted over the public power grid can also be graphed as periodic waves. A perfectly regular and symmetrical sine wave represents a very simple and clean example of a periodic wave. In the real world, however, periodic waves are subject to numerous influences that can affect their shapes. These can produce waves that display distortions and asymmetries, as shown on the screen. To understand how this happens, it might.
So due to my switching devices, right? So my voltage is now getting disturbed. Right? It's not actually. It's not a pure sinusoidal. We have seen pure sinusoidal waveform and textbook, right? So maybe online resources, right? by seeing original waveform like a power quality analyzer and power analyzer with the help of some instrument, right? You couldn't have that exact AC sensor waveform, right? So we have also we have we have seen our CRO, right? So in our colleges, right? So it's not actually, it's not pure science waveform. So somewhat it's going to be distorted, right?
It might be useful to work backwards and deconstruct this wave into its constituent components. A periodic wave, no matter how distorted, can be defined as the composite of a single primary or fundamental wave, plus one-third the fundamental. The second wave is therefore additional harmonics, results in further distorted wave, shown in our.
So if you are having that's called red color tools, it will be says that, right, it will be my pure sinusoidal waveform. It will be around 50 hertz in the sense, right? Now due to my those switching devices, right, you could see my second thing. So you could have the two waves, right? So இங்க பார்த்தீங்கன்னா எனக்கு ரெட் பார்த்தீங்கன்னா ஒரே ஒரு வேவ் ஃபார்ம் இருக்கு, ஒரு half wave form. But in my blue color you could see 1, 2, 3. So this is what my third order harmonic. So totally 6 இருக்கு பாருங்க, 4, 5, 6. This is what my total. எனக்கு ஒரு சைக்கிள் வர வேண்டிய இடத்துல எனக்கு 6 cycle வந்திருக்கு due to my non-linear loads. Non-linear loads in the sense we are using SMBS, right? Switch mode power supply in computer. We'll have variable frequency drive in our induction motors. ஸோ அதில் என்ன பண்ணும் பார்த்தீங்கன்னா, ஸ்விட்ச் மோட் பவர் சப்ளை அண்ட் வேரியபிள் ஃப்ரீக்வன்சி டிரைவ், என்னோட ஆப்ரேஷன் என்ன, உள்ள எல்லாமே ஸ்விட்சிங் டிவைசஸ், பவர்டானிக் ஸ்விட்சிங் டிவைசஸ் இருக்கும். It will based upon my electrical load demand, it will going to adjust its power supply as well as total power supply. It's going to adjust. இந்த கம்ப்யூட்டர்ல பாத்தீங்கன்னா ஹார்ட் டிஸ்க்கு ஒரு பவர் சப்ளை வேணும், ஹீட் கீபோர்டுக்கு ஒரு பவர் சப்ளை வேணும், டிஸ்பிளேக்கு ஒரு பவர் சப்ளை வேணும். My switched mode power supply is going to be convert my input power supply to 230 voltage. It's going to be converted to a different load. Different load க்கு different power supply delivery பண்ணும். So it only major role உள்ள என்ன இருக்கும்னா my switching devices. The same way, due to that my input power supply, it's now somewhat it's getting, right? So due to it's now my variable that's called my switching devices, now we'll have different kind of load consumption in my load side. ஸோ அதுக்கேற்ற மாதிரி ஃப்ரீக்வன்சி சேஞ்ச் பண்ணிக்கிட்டே இருக்கும் இல்லையா மை ஸ்விட்சிங் டிவைசஸ். தட்ஸ் வை மை இன்புட் வோல்டேஜ் இஸ் ஆல்சோ கெட்டிங் அஃபெக்டட் டியூ டு தி ஸ்விட்சிங் டிவைசஸ். தட்ஸ் வை வில் ஹாவ் டிஃப்ரெண்ட் திங். இஃப் மை இன்புட் ஃப்ரீக்வன்சி இஸ் நவ் 50 ஹெர்ட்ஸ், right? Input frequency is 50 hertz. So for example, this blue color is now 1 is to 6, sorry, 1 is to 3. That is called my total 6 hours. That is called 1 is to 3. That is called third harmonic. Fundamental frequency oda multiply varadu will called different types of harmonics. Fundamental frequency oda multiply varum. That is called third order, fifth order, seventh order, ninth order, 13th order. நிறைய இருக்கு, right? We'll see.
Our example. Adding additional harmonics results in further distortion in the waveform. The presence of all these individual harmonics can be expressed as total harmonic distortion, or THD. The mathematical formulas for calculating THD are shown on the screen. Fortunately, modern test instruments designed for measuring harmonics can perform these calculations automatically and display the result.
So these different kinds of harmonics, right? So third order, fifth order, seventh order, ninth order, 11th order. These are called odd harmonics. There will be even harmonics also will be there, right? So these are the harmonics which will be developed or maybe injected to this my network, electrical network, due to my operation, different kind of operation of about my switching devices, right? So how that switching device is getting changed on cyclically, right? So there will be a number of cyclic method will be there. So based upon that, there is a huge injection of harmonics into that electrical device will be possible, right? Anyway, I'm just going to show you one small video about measuring of harmonics by using a fluke meter, right? So it's a famous meter fluke. I'm just going to share that video. Now
Distortion
we'll
in
see how actually the power look like. One second. Now you could see that exact harmonics is now, which is now measured by real time with on lighting, right? So on CFL light is now connected with small CFL light is now connected. So அந்த லைட் வந்துட்டு எப்படி that is called compact fluorescent lamp, right? So அதுக்குள்ள எனக்குள்ள பார்த்தீங்கன்னா AC to DC conversion, the rectifier that's called இருக்கு. So due to that, now there is a harmonics is now getting introduced, right? We'll see.
In this video, we're going to cover how to use the harmonics test on the Fluke 435. We start by activating our menu and then selecting harmonics with my arrow keys. Confirm that by hitting the enter button, and we prepare the SD card for the test. Most harmonics are going to show up in amperage, so I'll use the F1 button to toggle the amps.
Now you could see third order harmonic, fifth order, seventh order. Now that fluorescent lamp, compared to fluorescent lamp, it will giving you about third order harmonics, right? So it will generate more third order harmonic over here.
And generate some harmonics. In this case, we can see that the third is the most prevalent, followed by the fifth and the seventh, indicative of a single phase power supply. If
60
I
hertz power
switch
supply.
my function on the demo board, we have more fifth now, which is indicative of a three-phase power supply. To see these signals, I can hit the scope button, and I'll toggle over the scope, and I can switch to amperage, and over to a phase.
Now you could see this is what my voltage, and this is my current, right? So the current is now having two bumps, right? So you could see.
So I can see phase A, my voltage being the larger sine wave, and my current waveform being the double hump that shows a three-phase power supply.
I will show you one more video. It will be a real time actually Ecogo, I think. It will be could easily understood, right? So he will just connect a one CFL light. He could easily understood lighting load harmonics. Straight away you're just able to have that thing. Yes, this one you could easily understood how actually on CFL bulb is now directly connected into the my power quality analysis. You could easily understood. Now I think I could see my screen. Yes, it's getting shared. Yes, Ekakova test and measurement device.
Hello and welcome to Yokogawa's video on how to measure.
So you could see there is a CFL bulb is now glowing over here. We are just going to directly measure harmonics which is developed by the CFL lamp. So this is CFL. In this bottom there is a power electronic device will be connected over here. The input voltage 120, 120 voltage, right? So current is now 173 milliampere. So total voltage is now consumed by the system is now 12 watts, right?
Harmonics. Chen, I'm the applications engineer with the test and measurement division. Today I'll discuss a little bit about harmonics and how to use the power analyzer to measure harmonic currents and harmonic voltages. Harmonic voltages and currents in electric power systems commonly cause power quality problems. Harmonics refer to all sine waves whose frequency is an integer multiple of the fundamental wave. A device
Yes,
operating
exactly.
at 60 hertz.
He just going to give you about over introduction about harmonics, right? So this is my original frequency 60 hertz. This is called my first order. This is my fundamental frequency input voltage. But due to my non-linear loads like my power electronics devices, there is a huge difference is now happening, right? So 120 hertz, 120, 240,
Hertz, hertz.
third order,
When the
fourth order.
occur in the equipment connected to the power line. Regardless of how common to a series of simple sinusoids using a Fourier series analysis, Fourier the frequency of the input circuit, the output of the PLL circuit. The measured result is a list of all the harmonic orders, including the process at 9,000 points. The measured result is a list of all the harmonic orders.
So this is a block diagram about my Ekokova harmonic analysis thing, right? So என்ன பண்ண போறோம்னா they are just going to connect two probe on my two leg, and there is a low pass filter and an analog to digital converter. There is a fast Fourier transform algorithm is now running on my embedded computer, and after that it's now having display scope over there, right?
Measured result is a list of all the harmonic orders, including the fundamental frequency and the RMS component at each order. Power analyzers are also capable of accurately measuring the total harmonic distortion, phase angle difference, power factor, inner harmonics, and more.
So in a CFL polarity bulb, I told that, so it will be around zero 0.6 power factor alone. You could see real time power factor. Right? Man, normal current will be 1 now current it instantaneous time. This is called 117 amp voltage, and the current is now 175 milliampere. Right? The total power is now 12 watts is now consuming. So now we'll have that voltage that is called harmonics. It will be 3.5%. Current pathina 73%. It will be somewhat very high.
More. Additional features, inner harmonics, and more. Additional features will also allow you to display the harmonics in a bar graph,
So you could see
vector
third order.
graph, perform harmonic analysis according to the international IEC standards, and more. For the most comprehensive harmonic measurement and analysis, a digital
So
power analyzer.
you could see my input voltage is now pure sinusoidal waveform, right? By my current consuming by this exact lamp is now it's not exactly pure sinusoidal current waveform. You could see there is a spike and there is a drop, there is a spike, there is a drop. So due to my power and switching devices, right? So that's why huge. It's not exactly sinusoidal waveform, right?
Analyzer is the ideal tool that will provide the best accuracy and ease of use. Thank you for watching Yokogawa's video.
So with that, I'm just going to phrase it today classes. We'll see different kind of loads and different kind of harmonic measurement. So இதெல்லாம் இருந்தா என்ன சார் ஆகும் நீங்க கேட்கலாம். ஸோ ஹார்மோனிக்ஸ் சார் ஆல்டர்னேட் ஸ்விட்சிங் டிவைஸ் யூஸ் பண்ணி நான் இன்கமிங் பவர் ரெடியூஸ் பண்ணி பிரைட்னஸ் இன்க்ரீஸ் பண்றேன். எனிவே பவர் கன்சம்ஷன் இஸ் நவ் கெட்டிங் வெரி வெரி ரெடியூஸ்ட் டியூ டு மை இன்கண்டக்ஷன் லேப்ல பார்த்தீங்கன்னா வில் பி அரௌண்ட் 100 வாட்ஸ் எடுக்கும், 200 வாட்ஸ் எனக்கு பிரைட்னஸ் அதிகமாக கிடைக்காது. டியூ டு மை சிஎஃப்எல் எல்இடி பல்பு எலக்ட்ரானிக் பல்லாஸ்ட் இருக்கிற டியூப் லைட் எனக்கு பிரைட்னஸ் அதிகமாக வருது. ஆல்சோ ஐம் ஜஸ்ட் கோயிங் டு ரெடியூஸ் பவர் சப்ளை கன்சம்ஷன் due to my using of electronic ballast over here and switching devices. But even though we'll have a number of advantages over using these type of technologies, right? So it's even every technology has its own advantage and disadvantage. So in the switching device advantage என்னன்னா நமக்கு power consumption reduce பண்ணுது, output increase பண்ணுது. But there is a huge disadvantage about my harmonics. So in the harmonics industry இருந்தா என்ன சார் நடக்கும் electrical network? People already study anyway. So due to my harmonics, right, if you're just going to inject more and more harmonics into the electrical network, inject பண்ணீங்கன்னா the conductor is now getting more what could I say? It's getting more getting heated. So more heat touchna the conductor is now connected with my transformer, distribution transformer. Transformer is also going to be getting affected. So more heat touchna transformer efficiency, you know, wherever the temperature is getting increased, definitely efficiency is getting decreased. அப்ப transformer efficiency decrease ஆகும். அப்போ டிரான்ஸ்ஃபார்மரோட எஃபிஷியன்சி டிக்ரீஸ் ஆச்சுன்னா மை அவுட்புட் டெலிவரி, ஸோ த டிரான்ஸ்மிஷன் ஆஃப் எலக்ட்ரிக்கல் அவுட்புட். ஸோ ஆல்ரெடி டிரான்ஸ்மிஷன் லாஸ் நிறைய இருக்கு. அகைன் டிரான்ஸ்மிஷன் லாஸ் டிரான்ஸ்ஃபார்மரோட லாஸ் வந்து அதிகமாக இன்க்ரீஸ் ஆகும். அப்போ டிரான்ஸ்ஃபார்மர் டெம்பரேச்சர் ரொம்ப அதிகமாச்சுன்னா டெஃபினட்டா இட் லீட்ஸ் டு ஃபெயில். ஸோ டிரான்ஸ்ஃபார்மர் ஃபெயில் ஆகும், கண்டக்டர் ஃபெயில் ஆகும், எலக்ட்ரிக்கல் மோட்டர் ஃபெயில் ஆகும். The same way power factor correctionக்காக we have introduced shunt active filter with the help of capacitors, right? So automatic power factor correction capacitor போட்டிருப்போம். அந்த கஃபெக்டர்ல கெப்பாசிட்டர் என்ன ஆகும், மோர் ஹீட் ஆகும். மோர் ஹீட் ஆயிட்டு என்ன ஆகும்னா கெப்பாசிட்டி இஸ் கெட்ஸ் கோயிங் டு பி ஃபெயில்ட். ஸோ தட் என்டையர் எலக்ட்ரிக்கல் நெட்வொர்க் இஸ் கோயிங் டு பி affected. So due to this harmonics. Anyway, next class we are just going to see different types of lamps with measurement and what are the ways to getting reduce this harmonics. எப்படிலாம் இந்த ஹார்மோனிக்ஸை ஃபில்டர் பண்ணலாம் அப்படிங்கிறத we are just going to finish it off about second module. So thank you all for listening. Thank you all. Thank you, Mahendran. Thank you.